Hello everyone, I am Patel. I am currently pursuing Masters in Mechanical Engineering. This is Kavish Shah. He's also pursuing Masters in Data Analytics. There is one more member along with us named Rushil Patel. Our team comprises three members and two mentors, Professor Paragisa and Professor Kale. They guided us through entire our project. Today, I will be discussing on a techno-economic case study named District Cooling System with Solar-Based Absorption Chiller. I will talk about one of the possible mitigation methods for carbon emission caused due to air conditioners. Here is the brief overview of my talk. I will give a background first, and that will be followed by concept visualization, technological and economic analysis, findings, complexities, and finally, it will be ended with conclusion. Beginning with the background, there are certain countries like India where weather conditions varies from location to location. As you can see on the map on the left hand side, in India, the weather differs from hot and dry, hot and humid conditions to the cold conditions. Majority of the portion of India is having hot and dry and humid weather conditions where temperature reaches to 40 degrees centigrade in peak summer. That can be seen on the another map. Therefore, the air conditioners are unavoidable necessity of the people living there. Some part like Delhi are also having composite weather conditions in which in winters temperature falls to almost zero. Therefore, not only air conditioners but heaters are also required in the region. Looking at the existing technology, window and split air conditioners are dominant in the market. In summer and monsoon, air conditioner unit account for 40 to 50% of electricity consumption. A significant part of carbon footprint is directly traceable to the use of window and split air conditioner because countries like India and China still relies on coal for electricity production. Almost two-thirds of their electricity is produced by burning coal. Fortunately, with the existing technologies, air conditioning can be provided with a smaller carbon footprint. Some of the example of those technologies are unitary split air conditioning system and variable refrigerant flow air conditioning system. The unitary split air conditioning system is commonly found in household, and the variable refrigerant flow is generally used at high-rise buildings, public spaces such as malls and restaurants. However, it is having slightly higher efficiency. It is not suitable for large-scale air conditioning applications. For large-scale applications, district cooling system is an advisable concept that consists of a chiller plant that produces chilled water, and chilled water is supplied to the consumers with a network of pipeline. A customer can be hundreds, thousands, small or big commercial or residential units with their individual air conditioning requirements. To produce the chilled water, the chiller plant requires low-grade heat energy. That need can be satisfied with solar energy with the use of various kind of collectors or biogas or sewage gas for an eco-friendly manner. For a continuous flow of chilled water supply, a chilled water or hot thermic storage fluid tank can be provided. District cooling system can be used with and either uh, either vapor compression refrigeration or vapor absorption refrigeration technologies. Unlike window and split air conditioning, it does not emit heat in the surrounding, therefore it reduces the heat island effect. In our case study, we consider a district cooling system with vapor absorption chiller plant that gains heat energy from the solar farm. In this schematic, you can see the entire uh, layout of the plant. In the left hand side, there is a solar farm that compresses parabolic trough collectors, and using that parabolic trough collector, solar heat is gathered and supplied to the thermic fluid. When the thermic fluid is hot enough to pass to the vapor absorption machine, it is transferred to the thermal tank to provide a continuous flow to the machine. Then it goes to the machine, and machine utilize the heat energy to produce the chilled water, and that chilled water is then again stored into chilled water tank, and that is passed to the consumers as per their requirements. In the entire system, the electricity is used for only pumping the fluid that does not consume higher amount of electricity. Therefore, the system has significantly lower carbon footprint than other systems. To entire, sorry, to design the entire system, we estimated cooling demand based on loads and environmental factors. For the heating loads, different parameters like transmission load, infiltration load, sensible and latent infiltration load, and internal load due to human occupancies were considered. The environmental factors include atmospheric conditions like solar availability and location, and a date and month of the year, because it also affects the temperature. Combining all the uh, combining all the analysis and study, the equipments like solar collectors, vapor absorption machine, thermic and chilled water storage tanks were sized and their financials were determined. To provide close to the reality simulation, a 13-story building with 400 meters square of floor area was considered. The derived equipment capacities for particular location can be found in given table on the right hand side. The carbon footprint was also calculated for different air conditioning systems like unitary split air conditioning system, district cooling system, comprising vapor compression and vapor absorption refrigeration system. The third system, vapor absorption district cooling system with solar farm, has the lowest carbon footprint to around 123,000 kilogram per annum. Talking about the economical aspect, capital and operating costs were derived and compared for the vapor absorption machine and vapor compression refrigeration based district cooling system. For determining capital cost, assets like land, building, parabolic trough collectors, WAM are considered. And for the operating cost, overheads like office overheads, raw material, electricity charges were taken into consideration. Furthermore, operating cost has been calculated for 20 years, taking into account inflation of 5% every year, and tax savings on the depreciation has been estimated at 15% rate according to the Indian income tax authorization. Also, government subsidy has been taken into account. Furthermore, to provide the viability of the project, we have calculated net present value, discounted payback period, and internal rate of return. The graph in the bottom corner represent the cost comparison between VAM and VCR based district cooling system for 20 years. From the viability analysis, it is obtained that capital cost of VAM is around 41% higher than capital cost of VCR. On the other hand, VAM saves approximately 63% in operating cost. The discounted payback period through the cost saving is 11 years and 3 months without any financial aids like subsidies from the government. The internal rate is also at 15% without any financial aids. By considering government subsidy, the discounted payback period shrinks to the 7 years and IRR increased to this 22%. In other words, if we say customer can recover the capital investment in 11 years and later they can enjoy benefits from the VAM for 9 more years. The concept has lots of benefits, but the benefits comes along with a bit complexities as well. The major complexities can be architectural planning for new constructions and implementing the same concept in older buildings as a retrofit. Moreover, there can be different additional cost associated with system installation, or there might be some hidden cost as well based on the locations. Even the project is demanding high amount of capital cost, there might be some chances for involvement of state or central government. And the major complexity is the district cooling system is an integration of several technologies, most of which are well established. The complexity lies in the acceptance by various parties, such as customers, manufacturers, and operators. Recapitulating all the findings and study, we can conclude that for providing air conditioning, a district cooling system with vapor absorption machine and solar heat input has the lowest carbon footprint, that is followed by VCR based district cooling system and unitary system having the largest. Despite having complexities to implement, this technology has the potential to substantially reduce carbon emission into the atmosphere. Thank you so much for listening to me. I would like to thank Professor Kale and Sa for guiding us for the entire project. And I would like to thank you, my team as well. Thank you.